Today, on how it's made. Wooden bowls. We're dishing out the details. Chainsaws. We'll show you how they make the cut. Stackable potato chips. We go to the factory where the inventory is piling up. And jet compressor blades. An idea that's really taken off. There was a time when bowl making was a cherished trade passed down through generations of families. But today, with so many inexpensive materials with which to mass-produce tableware, handcrafted wooden bowls have become a specialty item, and this centuries-old traditional craft almost a lost art. These exquisite bowls are made from a solid piece of hardwood, beech, maple, walnut, or cherry. Logs arrive at the bowl mill fresh from the forest, so they're still very damp. That's an advantage, because the moisture lubricates the cutting tools. The first step is to divide it into blocks. The chainsaw operator measures and inspects the log. The diameter and defects, such as knots or scarring, dictate the length of each block. He inspects the ends of the block, marking any cracks or other flaws with a red crayon. The ripsaw operator uses different size bowl patterns to determine the best way to cut the block. The goal is to get the most and biggest bowl size pieces possible without using the defective areas. Each bowl-sized piece is called a bowl blank. This block is large enough to yield 3 blanks, each one wide enough to produce a 43-centimeter bowl, and a series of progressively smaller bowls that nest inside it. They mount the blank on a specially designed woodworking lathe. From this point on, everything depends on the skilled hands of the lathe operator. As the block spins, he carves out the bowls using a series of specialized knives that this mill designed and forged. First, he uses this curved knife to shear off the outer portion. It takes great expertise to know exactly how to angle the tool and when to pull it out to release the wood shavings and prevent a jam. After 2 or 3 minutes, what they call the exterior bark shell is off. The bare wood that's left is the outside of the largest bowl that he'll mill from this blank. With a finer blade, he sculpts the wood to just the right thickness and smooths the surface. Now he switches to a smaller curved knife and cuts into the wood. This both forms the inside of the largest bowl and the outside of the next, smaller one. He repeats the smoothing and cutting process with progressively smaller knives, making bowl after bowl at a rate of about 1 a minute. This one bowl blank produces 4 nested bowls, the smallest measuring about 23 centimeters in diameter. The bowls are steamed for about 4 hours to draw out the sap and penetrate the pores of the wood, hydrating each bowl uniformly. That way the wood doesn't crack and split while air drying. Once a bowl is dry, about a month later, workers even out the top rim on a sanding table. Then, using a belt sander, they smooth the outside and inside surfaces. The bowl now goes upside down through a specialized knife that shaves off part of the bottom. This gives the bowl a flat base on which to sit and a place to inscribe the company name. Businesses can order custom-made bowls featuring their company logo. Artists burn the design into the wood or paint it on. or do a combination of both. The bowls now go for a bath in food-safe mineral oil. This nourishes the wood, preventing dryness and cracks. Oiling also brings out the natural beauty of the wood grain. And because every raw log is unique, no two bowls are ever alike. It's loud, it's powerful, and it rules the forest. The chainsaw has revolutionized the logging industry by replacing mortal muscle with mechanical torque. It's made the work a whole lot easier, so it continues to be a rip-roaring success. The chainsaw can set up any tree for a big fall and then chop it up. These machines start with the plastic housing. 3 aluminum inserts will be molded into it to provide solid anchors to attach other parts. A robot picks up the inserts one at a time and delivers them to an injection molding machine. The robot strategically places the inserts in a mold at the front of the machine. The machine then injects melted plastic into the mold to make the chainsaw's engine cover. During the molding, the metal inserts become integrated into the housing. It takes just seconds to transform these plastic pellets into a chainsaw engine cover. The robot carries each engine cover to automated cutters that remove any unwanted bits of plastic. The scrap drops into a bin below. A robot then places each engine cover in a special fixture to cool for about 10 minutes. Then it moves the part to the next station. There's one more piece of plastic housing, the fuel tank. This sonic welder melts and fuses it to the engine cover using high-frequency vibrations. Now they move to the engine and install a spring system for the starter cord. They slide the two-stroke engine into the plastic casing, and they pop in a spark plug. They lubricate the crankshaft, then install an automatic oiling system for the saw chain. They attach the carburetor and the starter system with the pull cord handle. They fit an air filter into its slot. Then they dip stud bolts for the chain bar in adhesive and screw them into the inserts molded into the plastic housing. They attach the rear handle and a trigger with a safety release. Then they screw the front handle into place. They attach a filter to the oil line that lubricates the bar and chain. It will strain out any impurities. Now they install bearings and the clutch system on the crankshaft. The clutch is the link between the engine and chain. When it's engaged, the chain moves around the cutting bar. The engine is ready for a test run at typical speed, 8,000 RPM. They adjust the carburetor so that it mixes the right amount of gas and air and check the exhaust to make sure it doesn't exceed pollution laws. They attach the trademark sticker and other operational information. Then they attach a brake system. Finally, they pack the metal bar and chain blade in a protective sleeve. Once the operator installs the chain blade, he has a power tool with teeth for any job, no matter how you slice it. It's a snack that's made to stack. Each stackable chip is made exactly the same, unlike other chips that come in irregular sizes and shapes. This uniform concave shape allows the chips to tightly interlock, so you can fit a lot of them in a tubular container. It means you get quite a stack of munchies. It's a case of production going down the tubes, because tubes are ideal containers for stackable chips. To make these tubes, big rolls of plain brown paper and foil-backed paper unwind. The foil will help keep the chips fresh. The streams of paper travel across rollers that coat them with glue. The paper layers twist around a mandrel that's turned by a big belt. The belt also presses the glued layers together. Next, the label paper gets a coat of glue. This helps it stick to the paper on the mandrel. A camera photographs the white edging on the label paper, then relays its location to a set of circular knives. They make a precise cut below the white edging. After each cut, the carriage moves the knives into position for the next one, cued by the camera. These paper and foil tubes head into a turning station. It's a box with a pathway inside that turns the tubes right side up. Hot metal heads curl the tops to allow lids to fit on. A roller pulls foil-backed paper into a cutter that punches out the lid shapes. Little vacuums take the lids to the tubes and heat seal them on. Plastic lids go over the paper ones. The lidded tubes are now turned upside down. They're ready to be stacked with chips. To make stackable chips, they use a ratio of 1/3 water to 2/3 potato flakes, with a little cornstarch mixed in. A conveyor delivers the mix to an auger which disperses it. Then it falls between rollers. Using 4 tons of pressure, they roll the mix into one long potato sheet. The potato sheet goes under a rotary cutter that punches out oval shapes. A device pulls away the scrap dough, leaving flat, uncooked chips. This scrap potato dough goes back into the chip-making operation, while the potato chips head into a fryer. As they travel through the fryer, rolling molds make them concave. The concave shape will make the chips stackable. The chips spend 11 seconds frying in hot oil. This makes them crispy. They travel under blowers to get rid of excess oil. The chips get a coat of seasoning, then do a backflip off one conveyor and onto another, falling into neat piles. A worker inspects the rows of chips. Then it's onto another conveyor that shakes them up to loosen the pack. They travel over scales, to portion them out for packaging. Automated spoons shove the chips into the open ends of the tubes. Guides tap the tops of the tubes to nudge the chips into position. Grippers then lower the stacked tubes to a station where spinning heads force metal bottoms onto them. Now they're ready for shipping. It takes about 20 minutes to make a tube of stackable chips. Soon, it will be empty and someone will be full. Compressor blades are key components in a jet's engine. The heart of the turbo machine contains thousands of them. They rotate 400 times per second, whipping air into small hurricanes. They compress the air, making it so hot and so dense that it literally explodes when mixed with fuel in the combustion chamber. In a jet engine, large compressor blades made of titanium compress the air entering the front of the turbo chamber. They move the air towards the back of the chamber, where smaller blades made of a nickel alloy compress it even more. The air heats up to more than 600 degrees Celsius, then combines with jet fuel, creating a powerful mix that explodes out the back of the engine. The blades start off as metal pellets called slugs. A ceramic layer prevents their surface from oxidizing when exposed to intense heat. The slugs are heated for 15 minutes in a 980 degrees Celsius oven. Meanwhile, a robot sprays lubricant on two forming dies inside a press. The robot retrieves the slugs and loads them in the first die. The press applies 1,000 metric tons of pressure to preform the metal. The robot then transfers the slugs to the second die, where they take the initial shape of the blade. The blades are then dipped in water to cool. The next robot cleans the metal burrs off the edges. The blade is now an airfoil. Robots will shape the rounded base, called the dovetail, later. The airfoil has gone from this to this. After a new ceramic layer is applied, the blade is once again heated in a convection oven to 980 degrees Celsius. Each heating and cooling cycle tempers the metal, making it more resilient. 1,600 metric tons of pressure gives the airfoil its final shape. A trimmer shaves off the excess metal. The heat turned the protective ceramic layer into glass. It'll come off later. It's taken an hour to shape the blade's airfoil. The dovetail, that nub on the right, is next. But first, this measuring machine inspects the airfoil. If any measurement is off by just half the thickness of a human hair, the blade doesn't make the cut. This casting machine will encase the airfoil in a matrix, a coating that protects the airfoil during work on the dovetail. They mold the matrix from liquid tin and bismuth. It solidifies into a metal cast around the airfoil. The future dovetail sticks out at the end. They load the cast into what's called a broach machine, with a series of teeth that carve the dovetail to its final shape. Now the cast can come off. A worker loads it onto the removal machine. A hydraulic cylinder hits the cast at its weakest point, breaking it in half. The finished airfoil emerges unscathed. A dot matrix machine punches identification numbers onto the blade. Next, they submerge the blades in fluid that penetrates any flaws in the metal. This inspection is critical because even the tiniest nick can spell disaster when a jet's engines work at full speed. They examine the blades under a black light. This blade is perfect. But spots of fluorescence on this one indicate microscopic cracks and weaknesses. This one gets rejected. The dovetail gets 2 strips of rubber silicone that ensure an airtight seal when the dovetail slides into its slot on the compressor drum. A final check, and the blades are now ready for takeoff.